Hello, guys. Greetings to every one of you, and welcome to our today's lesson. We are into physics, and today we are moving to topic 4, dynamics. With I myself, Sir Godwill Yakum. I'll be schooling you through dynamics today, and so I'll ask that you should be attentive. I'll equally ask that while you're taking this lesson, you should sit around with a notepad or your notebook, a pen, so as you take your summary, whatever I say that is very important, you take it down, and you can feel free to come back to this lesson anytime in order to exhaust it again, in order to understand more deeper. Yes, I am Sir Godwill Yakum, and I will be schooling you through dynamics. Like I said, we're going to start with momentum, then we'll move to Newton's law of motion. Let's get started. Good. All right, so I want us to start with momentum and Newton's law of motion. All right, so I'll start by trying to define what is momentum. Before we actually start Newton's law of motion, we'll look at law 1, law 2, and law 3, the applications, and then now we will come back to momentum again, especially we'll begin to look at impact. All right, so now momentum, I'll define what we call linear momentum. In physics, it's nothing with P. Linear momentum, we define this as the product of the mass and the velocity. Let me get my pen. All right, good. So what I'm saying is this. Good. This is it. Where momentum P is mv. Good. So now, since momentum P is mv, the unit of momentum is the unit of mv, which is kilogram meters per second. Good. So anytime you want to calculate momentum, make sure the mass is in kilogram and the velocity is in meters per second. That's said and done. You check here, you can see an example. They have given you mass in ton. They say the mass is 6.0 ton. Now you already know that 1 ton is 1000 kilogram. So 6.0 is 6000 kilogram. This is equivalent to 6 tons. All right. Okay, so the mass of the mass of 20,000 tons. That's an error I made. 20,000 tons. So 1 ton now is 1000. This makes 20 million kilogram. So good. Now let's look at Newton's laws of motion. So straight to the point, law 1. The first law, according to Newton's first law of motion, also known as the law of inertia. Newton's first law of motion is also known as Newton's law of Inertia. What is inertia? Inertia is the reluctance of a body to change in its state of motion. This simply means that when a body is at rest, that body will resist to start moving. When a body is moving, it will resist to change in its velocity. When the body is moving, it also resists to change in it. Actually resist to coming to rest, because coming to rest is also as a result of change in the velocity of the body. So now Newton's first law states this: a body will remain at rest or move with constant velocity unless acted upon by an external resultant force. Now, it means a body at rest will continue to be at rest. A body in motion will also continue to move with uniform velocity until, or a constant velocity until, an external resultant force acts on that body. Now, ladies and gentlemen, after looking at this law, we should go ahead to law 2. All right. Newton's second law is the rate of change of momentum. Good. So Newton's second law is the law of momentum. This law states that the resultant force acting on a body will cause a change in momentum in the direction of the force. The rate of change of this momentum is proportional to the magnitude of the force. This means that the rate of change of momentum, meaning that momentum over time, rate of change of momentum, we mean momentum over time, is directly proportional to what? The force. This is Newton's rate of change. So we'll say rate of change is delta P on delta T. Good. So this is actually Newton's second law of motion. Okay. So according to Newton's second law of motion, this law describes what happens when there is no force on a body. No. When law 1, is the law of inertia. When there is no force on the body, we are talking about the law of inertia. But in law 2, there is a force. This law explains what happens when a force is acting on a body. So the point you should underline is that in law 1, the law of inertia, until an external resultant force acts on the body. If external resultant force does not act, it means there is no force acting on the body will maintain its state of rest or uniform motion. Now, in law 2, when a force is acting on the body, that force is directly proportional to what? The rate of change of momentum. Now, prior to this, remember momentum is mv, right? Good. Mass time velocity. Prior to Newton's second law of motion, we can derive the fundamental relation of dynamics, FRD. And according to the fundamental relation of dynamics, summation Fi is equal to what? Ma. Good. It is from here that we have the equation F equal to Ma. Good. Where F is the resultant force. Good. We have a question to answer. The question reads: a golf ball of mass 45 grams. Take note, it's in grams, so you have to convert it to kilogram. Converting this to kilogram, you have 0.045 kilogram. Now, is putted along a level grain with an initial velocity u is what, or velocity, let's just put 4.0 meters per second. Okay, now it decelerates at a constant rate and comes to rest after. Okay, so I'll put u here. It comes to rest, so v is 0 meters per second, and after a time period of 3 seconds. Good. The question says calculate the frictional force on the ball. Calculate the frictional force on the ball. So first thing we have first of all done is we have converted the mass from grams to kilogram. Then now we are going to calculate the initial momentum, that's P1. So momentum is mass time velocity. Initially mass, we have the mass of 0.045, and then velocity u of 4.0. You multiply that, you have 0.18 kilogram meters per second. You now have to calculate the final momentum P2. Now, since final velocity is 0, it simply means that this final momentum must be 0 kilogram meters per second. Good. So now what is the change in momentum? Change in momentum is what? Final momentum minus initial momentum, which is 0 minus this. So delta P, which is a change in momentum, is equal to negative 0.18 kilogram meters per second. Now, remember, according to Newton's second law of motion, the force is directly proportional to the rate of change of momentum. So the force F is equal to what? Delta P over delta T. Delta P is negative 0.18, and delta T, what is the time again? 3 seconds. Good. Good. So when you take this, you divide by 3. Good. Divide by 3, you are going to have that we have a force of negative 0.060 Newton. Good. So that's it, guys. That's it. Now, since our force is negative 0.060 Newton, we have something to explain. We have to explain the meaning of the negative sign. The negative sign shows that the force acting is opposite to the direction of the velocity, or in the direction of motion. It means that if the motion is this way, this force is instead opposing the direction. And that's why we're calling it frictional force, because you know that frictional force opposes the direction of a body. And frictional force, remember, is a contact force. It is only applied when it's only applied between two bodies which are physically touching each other. Now, let's continue. Now we look at this question, and I read the question. A car of mass 1.2 tons. Remember, 1 ton is 1000 kilogram. So 1.2 tons should be 1200 kilogram. Good. Accelerate from, so we have u, accelerate from, we'll put v1. So v1 is, okay, v1 is there's not much space to solve, so we'll put v1 here and then v2 for 30. Calculate the average accelerating force on the car. So now you know that acceleration is what? Delta v on delta t, right? Acceleration. Okay, good. Acceleration is delta v on delta t. So it is v2 minus v1 over t2 minus t1. So v2 is 30 and v1 is 5. 30 minus 5 should be 25 over a time. The time is 7.5 seconds. Actually, this gives you 3.3 meters per second squared. Now, this is only acceleration, but the question is asking for the accelerating force. So now, you know that F from Newton's second law, F is equal to ma, fundamental relation of dynamics. So the F now is equal to ma, and that m is this mass, 1200 times 3.3. Yes, so this is what gives you 4000 Newton as an answer. Alright guys, so that's it for Newton's second law of motion. Yes, we'll now move ahead to Newton's third law of motion, which we all know as Newton's law of action and reaction. Good. So according to Newton's third law of motion, to every action there is an equal but opposite reaction. That's how many people they state this Newton's third law of motion, simply by saying that to every action there is an equal but opposite reaction. But a more preferred way will say, if body A exert a force FAB, if body A exert a force FAB on body B, then body B will exert an equal but opposite force FBA on body A, where FAB now will be equal to negative FBA. So they are equal but then they are opposite. That's Newton's law of action and reaction. Good. So you see an illustration of Newton's third law of motion. You see that the child is being pulled down by the earth with a certain force. That force is the weight of the boy. Then now, the earth is pulled up by the child with a force W, which is the weight of the boy also. As a result now, you see that the force acting down is equal to the force acting up. So that is action and the reaction pairs. Now, we'll look at linear momentum and conservation of linear momentum, which is going to lead us to what? LCM, the law of conservation of linear momentum. Good. Alright, so let's delve into full capacity for this part of our lesson, linear momentum and its conservation. Alright, now one of the usual result that can be developed from Newton's third law is that momentum is conserved in any interaction. This means that the total momentum of a closed system or an isolated system is constant. So some people can state this law as such: the total momentum of an isolated system is constant. That is, a system with no external force that's acting on it, the, the momentum is conserved, meaning that momentum before and after interaction is the same. All right, so now let's consider two bodies as shown in the notes on your screen. We consider two bodies that move towards each other, and then they stick together. They stick to each other after interacting, after their collision, they collide and then they stick together. Now you see that initially this is what was happening. These two bodies, they were coming closer to each other, but now finally the two of them stick together as one, and then they are now moving in this direction. Let's analyze what is happening. So now, good. I want you to know that if you want to find the momentum here, initial momentum, meaning that before collision, and the momentum after collision, knowing that momentum is just mass times velocity, you'll find out that the initial momentum is the same as the final momentum. So now, according to the conservation of linear momentum, the total momentum before collision must be equal to the total momentum after collision. You use this to really answer a lot of questions in physics. The total momentum of a closed system of interacting bodies before and after collision, or before and after interaction, is the same. All right. Now, I want us to also look at collisions in two dimensions. Yes. Good. For example, let's consider a head-on interaction or head-on collision where all the movement is in a single direction. Then they have a head-on collision with each other. Now I want you to know that in this kind of situation, the law still applies in the same way. The law still applies normally. The law of conservation of linear momentum. So we apply the law equally if there is a glancing collision and the bodies move off in different directions. In this type of problem, the momenta, in this situation, I'm calling momenta because it's already plural, must be resolved so that the conservation of momentum be considered in two perpendicular directions. So you resolve it to the vertical and the horizontal, as shown in the diagram that you can see on your screen. This is before collision, after collision. So after collision, now they just had a head-on collision. After collision, this is what is happening. They are now moving by like this. One is going this way, one is going this way. So that is why you have to resolve this. You have to resolve the two momenta All right, ladies and gentlemen, now let's analyze that. In this figure, you can see A, it has a mass, let's call it ma, and then its velocity, it has u, and then it's moving towards a disk B of the mass is mb. We consider that B is not moving. Now when they collide, after collision, A moves off with velocity VA at an angle of theta to its original velocity. Then B moves with velocity VB at an angle of phi to the original velocity of A. Now, after describing this situation, U is the initial velocity of A. So we have to resolve the final velocity of both spheres or both disks, and then we get those ones that are parallel to the initial velocity of disk A, which is of course u. So now you can see that the momentum before collision is only the momentum of A, because B was stationary. So when the body is not moving, it doesn't have momentum because velocity will be 0. So you see that we have just ma times u. Then now, after collision, we are now going to have ma. We're now going to have ma moving with velocity va cos theta, plus we now have mb moving with velocity vb cos phi.